Hello everybody, my name is Federico Politi and I run R&D for Characterization, and today I want to introduce to you the Legato memory solution and give you a demo, and specifically on the memory characterization portion of the new solution. The Legato memory solution is a comprehensive new product that covers several aspects and possibly all aspects of memory design, verification, and characterization. Specifically today I'm going to talk to you about the memory characterization portion and dive in a little bit into the details of how we generate the digital models for timing, noise, and power and leakage that are used in the digital flow, and also briefly talk about some of the verification, data manipulation, and the compiler integration that we provide into the new solution. Some of the main memory characterization challenges is that memories are become ubiquitous in the design. They occupy at this point 75% or more of the die area, and the current ad hoc solution to accurately model such memories are not good enough, and they don't contain enough details about the timing, the noise, and the power characteristics that are needed to describe these memories and to be used in a sign-off solution. The problem gets complicated as the number of PVT corners that we need to provide memory libraries for is increasing exponentially. There is a lot of sensitivity to process variation, so there is a need to actually model that in the libraries as well. And usually the memory are not designed and characterized in isolation, but they are obviously part of a compiler system where hundreds, if not thousands, of different memory sizes are characterized and need to be validated, and all the data that is generated out of this flow needs to be managed across different files, across different systems, across different users. An overview of the characterization solution: we start from TICO and SPICE input netlists. We go through several steps of static and dynamic analysis in order to reduce the original problem, which is a very complex problem given the size of such memories. We want to reduce the original problem into something that is manageable and that we can run accurate SPICE characterization on. So the idea is that we want to decouple the characterization step from the original size and make it independent from the original size of the memory we're trying to characterize. We call that process dynamic partition, and we use XPS technology to identify the worst case scenario for every arc that we need to characterize, and translate that worst case into a dynamic snapshot of the circuit that is small enough but still accurate enough to represent the original arc, and on which we can run full SPICE characterization. On the power characterization side, we use the full accuracy of the XPS solution by running the block at the top level. To give an idea of what dynamic partitioning means, you can look at these tables in which we show the number of, at the bottom, we actually show the number of transistors that we will use for a complete slew load or slew characterization for different type of arcs, and compared to the original size of 200,000 or more transistors in the design. And on the table above, we show you how much accuracy do we actually lose in this modeling step. We usually are below the 2 picoseconds, 2% in the worst case outliers. On the noise and the input pin cap side, we use a automated approach for characterization by carving out automatically the boundaries of the memory, and again using the characterization methodology and techniques that we have on the standard cell side to generate accurate CCS noise and ECSM noise models. I'm going to go quickly next to one of the new items that we propose into this new solution, which is what we call data manipulation system. The idea is that as part of these runs, there is a very large amount of data, as I was mentioning at the beginning, being generated. You have usually several dozens of different sizes for a specific compiler. You have hundreds of corners for every compiler. So the amount of data and that gets generated and needs to be managed is quite significant. So for this reason, we've introduced a new system that offers a Python interface to the data that we generate, and through that allows the user to use all the Python existing libraries for manipulation, data analysis, and visualization on the data. This is just a snapshot of some of the operations, query operation, modifications, copy operation, and visualization that you do with such a system. We'll see briefly a short demo of the same. As I was mentioning, we offer a Python interface to accessing the data that we generate, and we also, through this interface, we provide some of the basic functionality, such as the ones that are listed in loading, an LDB, getting a match, deleting, adding, printing items, and obviously saving and visualizing the data. These are, at the bottom of this slide, we show a very simple example of how do we get a specific entry in the library by providing a filter based on obviously the library name, the cell, the type of arc we're interested in, the pin, the direction, and so forth. After we get a match and the data extracted out of the library, we obviously have full access to all the lookup tables that the library, the specific match that we ask for, contains. This slide shows an example in which we have to correct a glitch introduced by the characterization, and how we can easily identify it first and then manipulate it to correct it. Another application, for example, is the user may ask us to modify the characterize hold times such that the specific constraints is satisfied. For example, that the hold plus the setup is greater than a specific constant. And again, it's very straightforward for the user to actually access all the data and create custom scripts to manipulate the results in any possible way is needed. Moving on to the validation portion, the basic idea is that we offer the user a way to validate the data that we generate. So one question that we get asked all the time is, how do you know that, for example, the setup and hold constraints, or the min pulse width, or the minimum period numbers that you put in the library actually make any sense? The idea is we automatically provide a way of setting up what we call a at-speed simulation. What that means is that we take the values that we have in the library for setup, for hold, and set up a simulation that uses those values to space the inputs appropriately. The same we do for the clock waveform, ensuring that the min pulse width, the cycle time are that come from the library are actually satisfied. After we have this run at speed, we compare the output of that run, the waveform of the signals of interest coming from that run, to the ones that are generated from a normal run, which is the one that assumes infinite setup, infinite hold, the same run that we use when characterizing. And so we need to ensure at this point that the behavior, obviously the timing and the waveform will be different because of the difference in relative setup and hold between signals, but we need to ensure that the functionality of the two runs is the same. And we have a way of generating waveforms for the debugging. We generate different outputs comparing the switching behavior of the nodes of interest. And nodes of interest in this case can be nodes that the user specifies manually because he's interested in two specific measurements, or a set of nodes that we know are usually important toward validation, and we automatically show the results on that. In the next set of slides, we're going to cover some details about the compiler flow. Another key component of a memory solution needs to satisfy the need of generating compiled instances out of a set of characterized ones. So again, given the number of different combinations of a specific family of memory, and given the number of corners that needs to be characterized and generated for a specific family of memories, most customers don't actually have the ability, the time, and the resources to characterize every single instance that they generate. So obviously there is a compiler environment in which starting from a pre-selected set of characterized instances, many more get generated with the different type of interpolation in order to cover the complete space. This slide shows you the main components of the compiler characterization solution. The user is able to define the axis on which interpolation is going to be performed, the definition of the instance that are going to form the base, my starting point from the interpolation, what are the PVTs that we will need to generate data for, and obviously the definitions of what arcs are we interested in. On the other side, he needs to provide obviously spice models and instant netlist for the instances we will actually run characterization on. After this is provided, the tool starts in parallel to the regular instance-based characterizations for the different characterized instances. These are some of the commands that are described in the interpolation interface. We define the compiler space, the PVT, what are the characterization instances, and actual characterization is supported with both on a defined memory flow or on a custom flow, depending on the user choice. And then the user will tell us what are the instances we want to interpolate to complete the space. Finally, after this is done, we will have a step of interpolation to generate the final library models. Here is just an example of what a usual interpolation flow looks like, and the axes are usually defined as the bit, number of bits, and number of words that we have in the memory. The characterized points are usually the boundaries of the space, so the 4 red dots in the slide. There usually is something in between as well, and then those main points are characterized, everything else is interpolated. The interpolation step again uses interpolation on the characterized data to generate the new data, and there are some specifics about the interpolation that we can cover. We build an equation, a function based on the data that we have from the characterized side, determine the coefficients, and then after we have that, pump through all the data to generate the interpolated libraries. There are some arcs that we do not do interpolation on, for example CCS noise arcs, but everything else, including CCS data, is interpolated. In the case of CCS data, it's not interpolated directly. We do a derivation to get to a voltage waveform, interpolate on that, and then integrate back to get current. To summarize some of the main benefits of our memory solution, ease of use is the first one, thanks to the automatic determination of probe locations, automatic measurements of delay and constraints, automatic partition of the netlist to guarantee the speed and the accuracy of the solution, and integration of third-party memory compilers and support for their memory characterization and interpolation. The accuracy comes from the fact that we can run full spice on the cuts that we generate, given the size reduction. The fast runtime comes from the full integration with the XPS solution, SPS simulation solution. And flexibility, because we allow the user to fully control the measurements that are taken, to fully manipulate the data in any way needed, support pretty much any memory architecture, and obviously give all the native interpolation capabilities or API, so to integrate with a memory compiler flow. Next, I'm going to give a brief demo to outline some of the main features that we discussed during this presentation. Specifically, I'm going to show how using the memory solution to characterize, interpolate, validate an SRAM macro, and then show some data manipulation examples and analysis on the results. Now moving to show you some demo on some of the elements that we talked about. From left to right, I'm showing some files related to the validation, to the compiler integration, and finally to the data analysis. So starting with the validation, as I was saying, we run two parallel runs, one at speed, one at infinite, assuming infinite setup and hold times, and a very large cycle time. And we are comparing the two runs to ensure that functionally the memory behaves the same between the two simulations. This first file, for example, shows what is the coverage that we can achieve given all the arcs that we are interested in, and what is covered and what is not covered. So this will give you an idea of, for every arc that you have defined, what actually is exercised in these at speed simulation runs, and therefore gives you the confidence that for that very arc, the library value that we generated in the library is used to exercise this arc in the at speed simulation, and therefore if the results match, you have a full coverage of your design. Some other examples of reports is a list of nodes of interest, in this case that the tool automatically extracts, and the behavior between the relax and the at speed simulation. So the idea is that for every node that the memory solution is able to recognize, for example, bit lines, core nodes, and pre-charge nodes, and all the internal nodes that we know are of interest for a validation step, they are compared across the simulation, and any difference will be reported in this file. Finally, the user has the ability to specify some of the nodes that should be compared, and through an interface that defines, all right, let me restart this. Finally, some of the nodes that may be of interest to the user to go through this validation step can be specified using the define measure interface, and the same define measure interface that is used for characterization can be used for validation as well. And so that's a way for the user to tell the tool, I need to know whether a specific node behaves differently between the two runs. So in this case, we have specified a measurement, and through the validation, specified measurement through the validation process, and we are reporting that results in these files here. And simply we're telling what delay table was used, what was the measure name that the user specified, and comparing the difference between the two measurements. In this case, no difference. Moving on to the next panel, where we're showing some of the interface that we use when we define a compiler run. So again, this should be very familiar to whoever is used to the characterization portion of the memory solution. In this case, we're just showing how we define the different axes and how do we define the different designs and the different PVT that take part in this interpolation, characterization plus interpolation stage. In this part of the demo, I'm going to show you an example of how the data manipulation system can be used to access the full library, how to access a specific entry and lookup table in the library, how to modify it, and finally how to display the result graphically before and after the modification. All these operations are contained into a Python script, and that can be run through Liberate MX through this simple command. To give you an idea of what this script contains, this is very basic set of containing very basic set of commands to load the library, find a match for the specific arc we are interested in, and then print some information about what was obtained, the specific lookup tables contain, and how to access that information. Add a conditional margin in the sense that we're going to add a very large number so that it's going to be visible in the final graph to one point in the table, one or more points on the table that satisfy a specific condition, and finally we're going to plot the results before and after. Simple command to load the Python script from inside the memory cockpit. And what you see on the screen following this command is simply a trace of all the different commands that we described. So here we're showing the first plot of the lookup tables, delay values for the delay arc that we matched and obtained from the library. In the axis you see the slews, input slews and output loads, and this is the behavior that you would like to see obviously in a characterized data where monotonically values are monotonically increasing with slews and load. After we do the modification of adding a very large number to those entries that satisfy a specific condition and redisplay that data, you'll see obviously that change showing up as a big discontinuity in the curve. That concludes my presentation. Thank you for your attention.